right, so today a bunch of Physics C kiddos came to me with a long problem that mathematically boiled down to this difficult integral, where y is a constant. This uses a skill called trig substitution, which is technically AP BC Calc, but doesn't really show up very much on the BC exam, so we don't spend a lot of time on it, and I'm going to walk you through how to do this difficult integral. Again, it is important to note here that y is a constant, so even though it looks like a variable, that there is a number. All right. So we're going to go through how to integrate this using trig substitution, and then I'm going to jump later in the video to some things that are and are not trig substitution and how you can hopefully spot whether they are trig sub or arc trig or u sub. But that's the deal. So let's walk through this ugly integral. So the idea behind trig substitution is that I really wanted to try u substitution, and I would like to make the bottom of this thing my u. But if I did that, right, so this is not u substitution, but if I tried to make it u sub, the problem I would run into is my u is x squared plus y squared, and again, y is a number, so my du is going to be a 2x dx. And where I run into a problem is that I have a 2x, and I just don't have a 2x up here. I don't have any x up here at all. It's a problem, so it's not u sub. When I realize that, and I conveniently see triggy things, okay, so the hint that it's going to be trig substitution is it's usually trig sub when you see something that is like Pythagish. And maybe you're going to argue Pythagish isn't a word, but I've just decided it's a word, so here we are. So I'm going to see something that usually has a square root and usually has something squared plus something else that is conveniently squared, which is the exact situation that I'm looking at here, right? And you might not spot that it's a square root right away, but I'm going to argue that this denominator is a square root quantity cubed. So that's Pythagish. Great. So the way I do trig sub is I want to replace this stuff, which I'm going to write as the square root of x squared plus y squared, all to the third, and a dx. I want to replace it with stuff in terms of theta. So I'm going to draw myself a nice little right triangle. And there's going to be a theta, and I'm going to have an x and a y, and the side that magically looks exactly like my Pythagish stuff. Right. So there are two basic steps to the process. First step is I want to replace the dx. The second step is I want to replace the ugly monstrosity that I have here. When I go to replace the dx, the rules for replacing the dx are to pick the easiest, oh, just a quick reminder, this thing's a number. The rules for replacing the dx are that I want to pick the easiest equation, like the easiest SOHCAHTOA, right? The easiest SOHCAHTOA of the equations, which in this case is going to be my x and my y, because I have to differentiate to get dx, and I don't want to pick a thing that's going to involve a quotient rule. I don't want to pick a thing that's going to involve a chain rule with that square root, so I want to pick the easiest possible version of this. So here, I'm going to argue that the easiest version of this is either tangent of theta equals opposite over adjacent, which would be y over x, or if your preference is to use cotangent of theta, you could have the x over the y. The advantage to picking the cotangent option is that the x is your variable and the y is your constant in this situation, so it might be nicer to have your variable on the top. The disadvantage is you just picked cotangent, and some of you are not as good at the derivative of cotangent. I don't know, I'm probably going to pick this one. If I pick this one, I would pick the x to the negative first. So if I do pick the tangent, remember, your y is just a number, so flip your x up. Don't do a quotient rule, just do a chain rule, right? So like either one of these is fine. I guess more people would probably pick tangent, so I'll pick tangent. When I go to find my dx, I'm going to differentiate the whole thing. So I'm going to get the derivative of tangent is secant squared theta d theta. And I'm going to get a y, because that's a constant, so it'll be times the -1 when I do the chain rule, so negative y times x to the negative second dx. And I want to replace the dx, right, because that's the thing I need to replace in this. So I'm going to clean this up a little bit and solve for dx. Again, this is not pretty, but it would be much uglier if I had picked another option, like if I had picked the one that would involve the root, or if y weren't a constant. And then I'm going to multiply the x squared over, so I'm going to get x squared secant squared theta d theta all over a negative y. And again, it's worth noting that this is a number, right? And this is my dx. Great, okay. So it's not the most fun thing in the world, but it's fine. I can deal with it, right? If I had chosen, I guess, to go the other direction, I think, like, this is fine. I think it might have been a slightly easier option to pick the cotangent. If I had done this instead, the derivative cotangent is negative cosecant squared. And on this side, I would have just gotten a 1 over y dx, which means that this ends up just being a negative y cosecant, oh, sorry, there's a d theta there, mea culpa, cosecant squared theta d theta. So I think this is better, right? The other reason I think that this is better is down here, if I go with this version, I'm still going to have to deal with this x squared, which I'm not stoked about. To deal with the x squared, I'd probably have to come back up here and simplify this equation, which I don't love. So I would have, I guess I'd make it x equals y over tangent theta, maybe. And so then my x squared would end up being a y squared over tangent squared. So it's not pretty. I think that it was a better option. I think it was a better option by far to do cotangent in this case, but either of those are fine. So all of that to say that that's my very first job. My first job is to replace the dx. My second job is to replace the ugly monstrosity that was here, which is this root x squared plus y squared all to the third. So I've already replaced the dx. This was job number 1. Job number 2 was to replace this. So I'm still using that same triangle that I drew where I had an x and I had a y and I had a theta, and this was the square root of x squared plus y squared, right? And we remember that y is a number. So now when I do job number 2, right, the trick is I really want to replace this stupid root that I am not a fan of. It's the worst. And yes, the whole thing's cubed, and yes, it's on the bottom, but I don't really care that much. So I want to pick the SOHCAHTOA that is going to use that value. So I want to pick SOHCAHTOA with that root and a constant. I don't want to mess with the x. I don't want to make my life harder. So I'm going to pick that with a constant, which in this case is the y. So if I want the trig identity that's going to involve the opposite and the hypotenuse, I'm going to pick sine. So I'm going to say sine of theta is going to be a y on top of this ugly mess of a root, which means if I divide the y over, I could use sine of theta all over a y to be basically exactly what's in my integral. I just have to cube it. So the integral has this whole mess cubed, so I would cube the whole thing. And I'm going to argue that I can replace the stuff in the integral with a sine cubed theta, sorry, that's a cubed, over a y cubed. That I would argue that replaces the stuff in the integral, right? So like that's going to be my replacement for the inside of my integral, which we would call an integrand if you want to be fancy. So that would be my replacement for the integrand. Okay, so now all of that put together, I'm going to add another one. So when we now put together the stuff I'm replacing, and it's probably going to involve me going back and forth a couple times because this was a lot of math. It took several pages when we did this in class earlier. So I'm here, and I know I'm going to replace this monstrosity, so I'm going to replace this piece with a sine cubed theta over a y cubed. Great. And I know I'm going to replace the other piece, and I'm probably going to argue you want to use the nicer version, right? Like, it's up to you, but I would argue it's better to use this. Up to you. Either one's going to shake out the same way, and it doesn't feel that way right now, but I promise either one's going to shake out the same way. So I should note that these are the same answer. Right? They're the same answer, it's just that one of them is a lot easier to deal with. So assuming I use the negative y cosecant squared d theta, so if we go back here and I use the negative y cosecant squared theta d theta, right? That's going to replace this piece. So I'm going to clean this up now, right? So that's what I've got to clean up. Well, I know the y's are just numbers, right? So remember, y is a number in this problem, and later when we do another one, I'll probably do it with like a 25 instead of a y squared, but here we are. So I'm going to argue I can pull a negative y over y cubed out because they are numbers, and what's left is a sine cubed theta cosecant squared theta d theta. Well, I know that that makes a negative 1 over y squared at the front. On the inside, I have a sine cubed theta times a 1 over sine squared theta. And what's going to happen here, which pretty much always happens, is all but one of my sines are magically going to cancel. And after all that disgusting, horrible work, I'm going to end up with a memorized integral. I know the integral of sine is negative cosine. So I'm going to get a negative 1 over y squared. This integrates to a negative cosine. And you might notice that I chose not to put bounds on any of these because this is a mess. And I don't feel like doing u sub or trig sub where I have to change my bounds that are currently in x's to thetas, and that's just going to be awful. So I just don't do that because why would I make myself suffer more? So instead, I just do it without bounds, and then at the end of the day, when I have to plug it into bounds, I set up my original integral and I just skip to the end and show what it would be if I evaluate it all together. So if I replace my cosine theta, or my negative cosine theta, remember we have to go back to that triangle we were looking at originally where we had an x and a y and a theta and this ridiculousness. If I replace my cosine theta with what cosine theta would be, well, that would be adjacent over hypotenuse. So this is a negative adjacent over hypotenuse, and I now have something where I can plug in the x values that were in my original integral. And I didn't have to do the thing where I changed the bounds because, again, changing the bounds from x's to thetas is going to be really, really awful because x is a number and theta, while also a number, is an angle, and you're going to hate it. So I would suggest just skipping it all together and doing all of this crazy integral work, which, again, was not a small amount of work. This took several pages, right? We took this page to replace dx. We took this page to replace the other stuff in the integrand. We took this page to actually put all the pieces together, and this is what I get. Now, if this is, in fact, an integral without bounds, which it won't be in physics, let's be honest, because it's physics class, not calc. If this was an integral without bounds, where I had this dx over this horrible monstrosity cubed, my answer would involve a plus c. So I would get, I think it was a negative 1 over y squared, and then I think it was a negative x over the square root of x squared plus y squared. We can go back in a sec to check, and I would put a plus c, right? But again, this is a calcy thing. You're not going to find that you're going to have a bunch of plus c's in general when you're doing this in physics. It's going to be contextual, so you're going to have values there. You're going to have values that you're plugging in. So if we just verify that that's correct, I think it is, that would be my answer. If I were doing this in physics, right, in physics, I don't know if they grade your calc in physics, but, you know, it is what it is. If I were doing this in physics, I would do all of that work without bounds, and then I would jump to, I also want to point out that in the physics context, and I don't actually have the thing in front of me, but when I did the problem in physics, there was a massive, ugly constant in front of the whole integrand. I don't know, there were K's, there were Q's, it had an L, there was a lambda, I don't know, man, I don't do physics, it was stuff, and all of that would have been in front of my integral, right? So it was that with my integral, and I think I doubled it and went from 0 to what we called L over 2, where L is the length of a fixed length rod that is giving you a charge of some kind, because I don't know, man, I'm not a physics person, I'm just trying to help you out. So I would integrate all that stuff with respect to x, so when I was all done with this, it would have the bounds from 0 to L, and that would be what I was plugging in, okay? I chose to do 0 to L over 2, rather. I chose to do that because if I have a rod where this is my center, and the rod is of length L, if this is L over 2 and this is negative L over 2, I would have the choice of either integrating from negative L over 2 to L over 2, or of integrating the convenient positive half and then doubling, because that's just how math works, because it's symmetric. Anyway, all of that to say, that is how I did this problem with 4 people during second and third period today. But again, without all the physicsy stuff, because I don't really know all the physicsy stuff and I wasn't going to look it up right now. So, quick way to eyeball whether something is trig sub or not trig sub. If you go back to the very beginning of this video, I mentioned that how I spot whether something is u sub or not is I say, well, what would I want the u to be and what is the du? So if we jump back here, this thing right here, this is u sub, right? I know this is u sub because if I made this my u, right, that x squared minus 25, my du would be conveniently have a 2x dx, and that x is on the top to cancel. So my du over 2x would be my dx. So I end up getting that this is the integral of a root u on the bottom. The x and the 2x on the bottom conveniently cancel, leaving me with just a 1/2. So I get that this is 1/2 the integral of a 1 over root u du, which is going to be a simple power rule when I rewrite this as a u to the negative 1/2 du, right? So this is simple u sub. I would up the power by 1, which would become a positive 1/2, right? I would divide by that 1/2, which is going to conveniently cut out this, and then I would add a c, because again, calc, not physics. So I would get that this is the square root of x squared minus 25 plus a c. Total u sub, no trig sub needed. Now the other one at the top is definitely trig sub, because I would want to do u sub just like I did in this example in blue, but it's not u sub because I don't have the x on the top. This looks Pythaggy, right? It looks like Pythaggy, Pythagish, I don't know, we make up words, right? It looks like a Pythagorean theorem. It is not arc-trig, which is going to happen on the next window, because arc-trig would have the 25 minus sine squared. So arc-trig would look like, or minus x squared rather. This would be an arc sine, right? Like this is an arc sine formula. This is not arc sine. You can't factor a negative out of a root like that. So I say, oh, this must be must be trig substitution, because it's not arc trig and it's not u sub. So I realized that this must be the hypotenuse because I'm subtracting the 25 from the hypotenuse. So x is the hypotenuse, 25 is one of the sides, and that would make the other side the square root of x squared minus 25. And then I call one of them theta. So again, I want to pick the easiest version, right? Remember what we talked about? I want to pick to target that dx, I want the easiest of the SOHCAHTOA equations, right? Easiest SOHCAHTOA equation every time. And in that case, it's definitely the x and the 25. I picked the constant and I picked the thing that doesn't have the root, because why would I want to differentiate with that root? So I say, oh, that's adjacent and hypotenuse, so I'm going to use cosine of theta is 25 over x, and I can either do the chain rule or the quotient rule like this, or I think I make my life better if I use secant. I really think your life's a lot easier if that x lands on top, right? I think this is way better. This is the one I would use. So if I'm using secant, the derivative of secant is secant tangent, right? So secant theta, tangent theta, d theta. And then this is just a 1/25th in front of the x. So I get a 1/25th dx. And you can see how little work there is in solving for the dx. I just multiply the 25 over, easy peasy, right? And I get a dx. So this is the first part of my arc trig. This is going to be a long page. Spoiler alert. Okay, so the second part of my arc trig is I need to replace that root 1 over, or the 1 over root x squared plus or minus 25. So the second part of my arc trig is I need to replace this, right? I want to replace this. And the way to do that is to pick the easiest equation, right? So again, we pick the easiest SOHCAHTOA that involves the root. We're not going to, so easiest SOHCAHTOA with that root and a number. I want to pick the thing that's going to be the easiest. So if I go back up to my triangle, the root is the opposite side, the number is the adjacent side. I want tangent, right? Because, so again, if I fix my, my root was the, and this is all about which side you drew things on. Like some of you might have put the, some of you, did I put a 25 here? That's not a 25, friends. That's a 5. Let's go back and fix it. At some point, some of you are going to catch this. That's a 5. Sorry in advance if some of you already caught it, that I can't math, but we're not going to redo a video because I can't math. So this is a 5. Okay, so, so I'm here. I want to use tangent, right? So I want my opposite over my adjacent. If they had been reversed, if I had put my 5 on the vertical side, then I might want to pick cotangent. Like I want to pick the thing that makes my life the easiest. Oh, actually, I take that back. I want to pick cotangent. Silly me. I want this on the bottom. So I'm going to pick cotangent because it's going to make my life a lot easier if that thing is already on the bottom, right? So it's already on the bottom. I'm going to divide the 5 over, and I'm going to get cotangent theta over 5. And oh, look, that's exactly what's inside the root. Like this is the exact integrand. So now, if we put all the pieces together, I'm going to replace this piece, right, this piece right here with a cotangent theta over 5. I'm going to replace the d theta, if we go up to the top, with a 5 secant tangent d theta. Sorry, replacing the dx with a 5 secant tangent d theta. The 5's conveniently cancel, and now I'm just on like some serious pre-calc action where I need to simplify my trig. So cotangent is cosine over sine. Oh, I don't even have to do that. I'm silly. Ooh, this one's a little bit tricky. Cotangent and tangent are going to magically cancel to 1. So I could make this a cosine over a sine, and I could make this a 1 over a cosine, and I could make this a sine over a cosine. Right? That's a cosine. But these are going to cancel, and these are going to cancel, and I'm going to be left with the secant anyway. Now, the reason I said, ooh, that's tricky, is that most of you actually don't know the integral of secant off the top of your head, which is understandable because it's a little bit tricky. So the integral of secant is actually really hard. Like this is, so this is a derivative that might be worth memorizing. It's a little bit tricky if you're not used to it. So essentially, the integral of secant, which I wasn't expecting when I walked into this, but here we are, so it is what it is. So to integrate secant, it's going to be the natural log of secant x plus tangent x, I think. We're going to double check. So I believe that this is the natural log of the absolute value of secant plus tangent plus c. But because sometimes my memory fails me, I'm going to do a quick check and I'm going to differentiate this. If I do the derivative, right, I would get 1 over the stuff, so secant theta plus tangent theta, and then times the derivative of the stuff. Well, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. And you might be thinking, Hogan, there's no way that's going to be a secant when it all cleans up. But I'm going to argue that there's a GCF of secant on the top. I'm going to argue that if I factor out a secant GCF on the top, I'm going to get a tangent plus the remaining secant, and that's all over secant plus tangent, and I'm going to argue that secant plus tangent and tangent plus secant are the same quantity because addition is commutative. So these cancel, and I get that that's a secant. So after all that quick little bit of checking, because that's not a derivative I do all the time, or an integral I do all the time, rather, I'm going to get that after all that work, this is the natural log of the secant of theta plus the tangent of theta inside an absolute value plus c. Right? Like that's going to be my integral. So then I'm going to have to go back and I'm going to have to look at my pretty little triangle, which is up here, and I'm going to have to replace secant with what it is and tangent with what it is, and that's going to be my answer. So I'm going to get the natural log of, if I go up to secant, secant is the hypotenuse over the adjacent, so that should be an x over 5. So this should be an x over 5 for my secant, plus, and my tangent should be opposite over adjacent, so that should be the root x squared minus 25 all over the quantity 5 plus a c, and that's my answer. Now you can see the difference, like the disparity in the work level, right? I would argue this was not an easy U-sub problem, but it wasn't a hard U-sub problem, and it took maybe half a page. And you can see the disparity with trig sub, which is why everybody hates trig sub. But we're going to do a little bit more because it's good for you. This one actually doesn't involve trig sub, and that's kind of part of the trick. So when I look at this, trig sub should be your last thought when something is like Pythagoras. My first thought is, could it be arc trig? And the answer in this first one is absolutely, this is arc trig, right? When I integrate du over root a squared minus u squared, that's an arc sine, right? So this integrates to the arc sine of u over a plus c. That's this exact formula. This is my a squared, this is my u squared. So my du is conveniently dx, right? Because my u is x, so my du is dx. This is 100% just arc sine. Almost no math involved. This is the arc sine of x over 4 plus c. Very little math involved as long as I know my integral rules and I can spot an arc sine. This one is going to be classic U-sub because, again, the first thought should not be trig substitution. It's horrible. It is the only way to do certain problems, but that doesn't mean it should be your first thought. It should be the, I've tried everything else, and oh my gosh, I hate my life, it's trig substitution. That's where this should be happening in your brain. So, sure enough, here's the x I wanted to cancel with this x, so I am set. This is definitely U-sub. So I'm going to get that this is the integral of an x over root u times a du over a negative 2x. So basically this is very similar to the problem I did before, except it's a negative 1/2 instead of a regular 1/2. It's still u to the negative 1/2 du. I'm going to up the power by 1, which is going to make it a u to the 1/2 divided by 1/2, which is conveniently going to cancel with this guy except for the negative 1. And then plus c. So I'm going to get negative root u plus c, and my answer should be negative the square root of 16 minus x squared plus c. Neither of those two involve trig sub, which is awesome. So that's my sort of quickish but not really quickish video on trig substitution. Happy to help if some folks in physics C want extra help, even if you're not in my AP class, because math is cool. The end.